And the second will be from Dr. Andrea Mario Vergani, one senior scientist and one young scientist. And we are very grateful for having them into this second webinar, and we thank you very much. And actually, the presentation will be recorded because it will be then available in our cost action website. And I think we can start. Julia probably has some problems, and I can be in some ways a substitute of the moderator till Julia is back. And also there is also Adna Asic. She is involved in the cost action as working group 5 leader with a role of science communication leader. And we are here and to share this initiative with many of you. So, Andreas, the floor is yours, and thank you again for having you here.
Thank you. I will share my presentation. Can you see me?
Yes.
Okay. It's in presentation mode, correct?
Yes. Go
Perfect.
ahead.
So my name is Andres Legara. I work for Council on Dairy Cattle Breeding. This is the third or fourth incarnation of a talk that I prepared originally for ADSA in 2022, I believe, with Ole Christensen, who works at Aarhus University. And this is about how to use omics features, but then we expanded to high throughput phenotypes for genetic improvement of animals. So, and this is basically all the material, all the algebra, the examples, everything is in these two papers. The first one is a paper in genetics with all the technicalities of the method, and the second one is a kind of a short review that I did for GDS communication. This is just a motivating example. So this is the US genetic trend for protein for Jersey, and then one of the health traits, retained placenta. Retained placenta positive is good, which means that it's been slowly deteriorating, and clearly we have some traits that are more difficult to improve than others. And one of the difficulties is recording, other one is heritability. So how can we do better? And it's been often said that we should stop using so much the black box and understand a little bit more what we do and to look better into biology. So then people tried, and one of the things that they tried is to use how to say, annotation, biological prior annotation, sequence. And after a few years, it didn't work very well. There was lots of trials in 2015, 16, 17, until a few years ago. And basically what happens is that you can work out that you find some gains, but they are small and depend on the trait. And then there's something that is kind of tricky, is that it's easy to do things for traits that are well recorded. So it's very easy to find QTLs for protein yield, but you don't need anything for protein yield because it's very easy to improve. So by construction, you improve even more traits that are already good, easy to improve. So then I wanted to introduce something else. Is now we have another kind of measurement, which is not exactly what your network is about, but I want to put both things because they share kind of methodological ideas. And one is, okay, we have these high throughput things. So you have accelerometers, you have podometers, you have milking robots, and they record all kind of things basically continuously. So you have these huge tables with numbers, basically. And then if you do some kind of review, you see two kinds of paper. The papers on the left is extremely biological, and frankly speaking, I don't know what they mean. So there's something called the RNEI Argonauts, or the Interlog Interactome, So I don't have any clue what this means. And on the right, you have things, okay, we did so many measurements in so many animals, and we try to make sense of this. And after you read these papers, you have a feeling that people is trying things. And you can not really develop new ideas just by trial and error, or let's try this with this data set, let's try that with that data set. The results are too much depending on your data set that we have. And it's good to have theory. The theories are often kind of approximations, but they help understanding. And in this, Ole Christensen realized that you need a theory in particular to work with RNA-seq. And then we realized that this theory could be extended to this high throughput phenotyping. So we need a theory to accommodate both things. And we also need a theory that says, okay, you can predict things based on RNA-seq or microbiome or whatever. But what you predict, you need to then detach the genetic part that can be selected from the environmental part that cannot really be selected. So this is, can't remember where I took this from, but this is some counting of phylum in microbiota, I believe. So it's just species abundance, but I mean, you just have rows with animals and columns with many readings. And you have many examples of this. You have RNA-seq, you have metagenome, you have accelerometers, you have milk flow, you have milk infrared spectrum in milk, you have near infrared spectra in seeds, and there's even more things, but they all look kind of similar. So you want to use this. You want to say, okay, I want to integrate this into a pipeline, and this pipeline will improve my prediction in some trait. But actually, the thing is that you have too many things to try fixed effect regressions. It's just too complicated. And you can estimate genetic correlations and say, okay, my mastitis, whatever, it has a genetic correlation of 0.6 with this particular microbiota in the rumen, but you have so many of them that you just quickly get lost. So we thought that one should come up with something. So what is the state of the art now? The state of the art is basically you prepare, you have some kind of experimental farm. In that farm, you have animals that you can record basically everything. And those animals, you also record, for instance, RNA-seq or milk infrared spectra or microbiota. So you have the trait that you want to improve, and then you have a proxy measurement. And then you say, okay, you take your proxies, and you have many of them, and you get an equation to predict your trait, and you are happy because the prediction is 90% accurate or something like that. And then with the same equation, you go to all your commercial farms and you use that equation. And then you get for each farm and for each cow, in our case, you get a prediction of the trait that you want to improve. So let's say that this is feed intake or methane. So this is how Canada is doing genetic evaluation for methane emissions, and it's well described. And you can go to this site and you can read how they do. But in my opinion, this thing has problems, and the problem is kind of obvious. And when you think on it, and it was shown in this particular paper. Basically, if you do a prediction equation based on some kind of complicated recording with many possible values, the prediction equation will work very well in your farm, in your experimental herd, but it doesn't necessarily work in other herds because you just found one that fits very well, but there's no reason to fit other things. So for most traits, it's almost impossible to develop a prediction equation that works across all possible farms unless you have data sets from all possible farms. That thing is probably only possible for very simple components like just fat or protein or lactose, but not other things. Now, you have kind of the same problem if you go for I'm going to find the most correlated biomarker. Basically, you are overfitting your data set. You think that let's try the best one, and the best one is just by chance. There are 100 not very good ones, or just good, and one of them is good just by chance. So you think this is the best one, but it's the best one in your dataset, not in other datasets. And this is what the statisticians call overfitting or cherry picking. So the plan is basically now the plan of my talk is, okay, let's try to create an actual theory that we can use for this purpose. And then when is this useful? And then some kind of concluding remarks. So this is the key idea. The key idea is you have DNA. The DNA produce RNA sequence, for instance, during development, that RNA seq is going to create some metabolites or to regulate something, and that something will create your phenotype of interest. So for instance, in growth. And there are some papers that have kind of the same ideas, but not completely formalized. So now you can convert this into an actual model. So you have three parts. You have genetics, you have phenotype, and you have your omics. And I put big M for omics because in the paper we use M for omics reading. And then we put arrows. What do the arrows mean? The arrows mean, okay, you have an omics. So when an animal is developing, the DNA, the actual genes say, oh, this animal is going to be big or small. I'm just kind of a cartoon, but I will produce this or that RNA seq. But the RNA seq is itself produced by some DNA coding. So the genetics create an omics. Now, the RNA seq is not stable, it's not just always the same, it's affected by some environment. So you can say, okay, my omics measurement, the gene expression of gene whatever, is equal to a genetic breeding, to a breeding value, because the gene expression is a number, is composed by a genetic part that is dictated by the DNA plus an environment, a residual, that comes from somewhere else. And now in the next step, the phenotype is created by this omics, by the RNA seq, and each RNA transcript has an effect, and that effect can be quantified in alpha. So if you have plus 10 of RNA seq gene whatever, then that will make 50 grams per day more, something like that. So the phenotype is composed of this effect of the omics, which is M, which is the reading of the omics itself, times alpha, which is the effect, this kind of a regression effect, plus a part that is genetics, but has not been codifying the omics because we could not read the omics or we don't know how it works. And then some other environment, some kind of residual, the farm or whatever. So this alpha coefficient, they just measure the strength of association of omics on the phenotype. You have a reading for some RNA seq for some gene, but in that particular trait, it's not doing anything. So you just have a 0 in this alpha. So this is actually a quite simple model, but it's reasonably easy, in our opinion, to understand, and it can be estimated. So you translate this into linear models. First, you have a model. So we start from the phenotype because what we see in animals is the phenotype, right? We see, for instance, growth and say, okay, I'm going to equate my growth, so the phenotype, to a function of my omics, and I can read my omics, and then an effect of the covariate, and then an estimate of the effect of each omics, and then a residual. But then you say, okay, I can do this. I can solve for alpha, beta, whatever. But then you have your omics, which is M, which is, again, it's just a columns with different readings for each gene. And each of them is a different omic phenotype. So can you say, okay, my new trait is a gene reading, a transcript reading, and I'm going to put this again into another linear model. So each omic reading, it's affected by some effects, including a genetic effect, which is my G there, and then a residual. And then you combine these two things. So what is the overall breeding? At the end of these two boxes, one inside the other, what is the overall breeding value? The overall breeding value is a sum of two things. You have on the most right, you have the genetic part that did not affect your RNA seq, but in fact did affect your phenotype. And you don't know exactly how. If you could do everything perfectly, probably you could mediate almost everything by RNA seq, but this is not the case. So you have that thing which is called AR from residual, I believe, or non-mediated. And then on the left, you have this summation of G and alpha. So what is the G? The G says, okay, the genetic effect of this guy is plus 10 for this transcript compared to the genetic effect of that other guy, which is -2 for that transcript. But now the transcript itself has an effect, which is this alpha. So you need to weight the transcript by the effect on the final phenotype. If the transcript is useful for, plays no role for this trait, the alpha will be just 0. And then, so an explanation, verbal explanation. So we have genes, right? Some genes will cause omics. So in development, you will have some genes that will say, oh, you are going to create this much of this transcript for this gene, this much of that transcript for the other gene, and so on. So basically what we do, if we could look at genes, we would just look at genes of individuals, say, oh, this one is creating +10, this one -5. And then you weight that for the effects of the transcript on the phenotype. That's a mistake, not on the genotype, it's on the phenotype. And that gives you a breeding value that is kind of omics mediated. And then you have other genes that they don't mediate through omics, but they still affect the phenotype. And because we fit everything together, we can tell apart the genetic part that is mediated by omics from the genetic part that is not mediated by omics. And this is what we call non-mediated breeding values. So you have these two kind of chunks. How do you estimate this thing? You have two flavors of methodology, and depending what you find more convenient. The first flavor is you can run an omics plot in which you estimate these alpha effects explicitly. So you say the transcript number 16, when it increases in 2, in 1 it will create plus 50 grams per day, more or less, or whatever. Then you have flavor number 2. Flavor number 2 says you are going to construct a matrix of similarity of animals, and this is just based if they share the same omics or not. And you're going to send that into some machinery, and that machinery will say, okay, the omics-based effect of this individual all summed together is some value. And this is similar for the people that do genomic prediction to GBLAP and SNPLAP, basically. Anyway, you choose one of these flavors, basically, because they are equivalent, so it's just for convenience. And once you choose it, you still have two things to run. It's two nested single-step GBLAP. And before we go there, one thing that we developed for the paper is that you can explicitly consider the case in which you have some animals have phenotype and other different animals have omics. So my example is that you could measure RNA-seq in liver in some animals. So then you need to slaughter them, usually. And you could measure feed efficiency in related animals and then analyze everything together. It's probably not very accurate, but the mathematics is correct. Anyway, you have this estimation method. So I said that you need to run two nested single-step GBLAPs. So this is the first one. You write my phenotype, which is y is equal to something, and this something is equal to u and I. And can I use the pointer here? I can probably use the pointer. Laser pointer. Okay. So in this model, you fit two kind of effects, basically. You fit a breeding value that is not mediated by the omics, and then you fit something that is mediated by the omics. How do you include the omics? You include an omics-based similarity, which is this matrix M prime here, which is a measurement of how animals are similar or not according to gene expression, for instance. And the result of this omics-based similarity is this U hat, and this U hat is basically the animal effect for that trait, but that animal effect is not genetics, it's omics-based. So it's essentially a prediction of what the part of the animal due to omics would be. And this is just other than that, this is just a regular mixed model equations, and we know how to solve this. Now, this model is exactly the model that people use for metagenome studies. So there is this very well-known paper by Gareth Difford, in which they use metagenome and they talk about microviability, and it's exactly this model. And there are other papers from other authors. Now, once you run this, you go to a second model. In the second model, you say, okay, I take my prediction of omics-based phenotype from the first one. So this is already an estimate. And you plug it here and you put like if it was an actual trait, an observation. And then you have a model in which you just have genetic relationships. And from here, you infer this A hat. So what is this A hat? This A hat is finally from the part that is explained by omics, the part that is explained by genetics. So basically what we are doing here, we take an omics prediction and we are separating the part that is genetics from the part that is non-genetics. And that was basically the missing part in all the existing theories. So, and then you just sum both. So you run your analysis one, your analysis two, the analysis one, you get this AR here for analysis two, which is the non-mediated. For analysis two, you get this A hat M here, which is the mediated. You sum this, and the end is the total breeding value. So, okay, this is the key message one. It's very easy to fit models with omics, and you have a bunch of models with them. But if you want to use this model for genetic improvement, you need to have a tool. It can be this model that we propose, it can be something else, to separate what is heritable from what is non-heritable. Because if my omics are affected by the environment, I cannot transmit them to my descendants, basically. Okay, a byproduct of this model is the decomposition. How much time do I have, Luca? Still?
A few minutes, but
Yeah.
just complete your presentation. Thank you.
Okay. So this thing led to something that we call the composition of the variance. So that was very typical when people estimated microviability. So you have a trait, it has heritability 0.30. Then people run this microviability analysis and they got microviability of 0.40. But then when they did that, they realized that heritability decreased. And they say, oh, there is a 10% decrease. And that is because part of the genetics went to microviability, but no one knew exactly how to quantify that. And actually, we came up with one equation, and the equation is this one. You have the total heritability of the trait, and it decomposes into two chunks. The chunk to the right, which is this thing, is the part of the heritability which is not mediated by omics. So if omics do not play at all any role in this trait, the heritability to the left and the heritability to the right h squared would be exactly the same value. But then the thing in the middle, it has two components. The first one is the this word is difficult. Microviability. So it's the fraction of total phenotypic variance explained by omics. So it can be pretty high. But then this thing is weighted by the heritability of the omics, which means that omics can explain a lot of the trait, but not necessarily they need to be heritable. They may not be heritable. Now, in turn, this translates into accuracies. The heritability of the trait is a measurement of accuracy based, or it's just the accuracy based on phenotype when you want to select animals. The fraction of total phenotypic variance explained by omics is essentially the accuracy of omics effects, how well you can appreciate your omics effects. The heritability of the omics is, if I knew the omics mediated part, how much of that is genetics, so the accuracy of that part. And this one to the top right is again the accuracy of the non-mediated part of breeding value. So omics can explain a lot, but they may not be useful for selection. And I will go again into that later. So coming back to our example, what happens if you do the mathematics is that solving the equation, the heritability of our microbiota levels would be 0.25. So it's not very high, it's not zero either. And the ideal omics measurement is basically something that is heritable, because then you can select based on that. And it needs to explain a good variation of the trait, because then it's similar to the trait that you're seeing. So one example of something that is reasonably heritable is milk infrared spectra. They have heritabilities of roughly 0.5. I cannot remember the heritabilities of RNA-seq, but I think they are kind of low, 0.05, 0.10, 0.15. But I'm not a specialist. So I just repeated myself. From here, you can also work out how much is the genetic correlation of something that I predict with omics and something that I actually see. So for instance, if I wanted to predict methane emissions with omics, and if I can measure methane emissions, then I know that the genetic correlation is this thing. So it's basically the heritability of the omics times the microviability. And that goes between between -1 and 1. Another example of this kind of reasoning is, okay, people say that when we can predict lameness from accelerometers. So I just pulled together here 3 numbers to make the example. So the heritability of lameness is 0.08, 5, 10, depending. In this example, is 0.08, so it's low. You can predict lameness using accelerometers with a predictive accuracy of 0.71. This is a correlation, so the microviability, but it's the accelerometer ability, it's 0.50, more or less. And now the heritability of accelerometers in horses, which is the only thing that I could find, is 0.09. If you put everything together, you can get an estimate of genetic correlation between lameness predicted with accelerometers and lameness actually observed, and it's 0.75. And it's actually not bad. But I mean, you don't take this seriously because the 3 papers are completely different data sets, so this is probably wrong. But this is the kind of reasoning that one needs to have. And then, using these considerations, we get the small examples when this could be useful. And these are really toy ideas. And basically, we assume a very, very large data set here in which omics can be very well estimated. So my example is basically composed of 2 animals. This is first we have a cow, and it has a single record for a phenotype. So the real reliability of the breeding value is just the heritability. But then we have a heifer. The heifer has not calved yet, but we could omics phenotype her, and then you can work out that the reliability of the breeding value is this thing, which is, well, the heritability of the mx to the square times divided by the heritability times microviability, whatever. And then you can make a plot in which this thing here, the reliability based on omics, is more reliable than reliability of using the phenotype. Now, what you want for selection is early measurement or more reliable. And you can make a figure. The figure is for a trait with heritability 0.1, right? So in this space of heritability 0.1, you can have a percentage of variance explained by the omics, and then the omics itself can be heritable. But some points are impossible. Because of the equation, you cannot have heritability 0.1 and then 100% variance explained by omics and omics 100% heritable. That is just impossible. So we have this core space here. And the black line is the line which separates 2 regions. In the bottom region, to the left, bottom left, omics are less accurate than Y. And in the top right, let's say, omics are more accurate than Y. And then the more red means more accurate. So basically, what you see is that we want to be in the top part. We want a very heritable omics measurement, and that explains as much as possible of the trait. So we want a good biological predictor of the trait, and we want a predictor that is heritable. So, for instance, a good point could be 20% of this C squared and almost 100% heritability, but it could also be here 0.3 variance explained by omics and 0.4 heritability. That also could be reasonable. So this is a sort of a conclusion. Well, the first conclusion is that the theory needs really to be tested. There's just a couple of papers that tested it, and the reason for that is basically that there are not many data sets in which you can test, and it's not easy to test. Then finding a good omics or RNA-seq or whatever based on biology that requires lots of measurements is difficult because it needs to be heritable and it needs to predict the trait well. And both things are different. But at least we have a theory, we have a framework in which you can trade things and you can say, okay, I have these transcripts, but they are very low heritable, or I have this biological measurement that I didn't think before, but it's very accurate to predict the trait. So at least you have some tools better than pure trial and error. I am personally skeptical, but I think it's also because lack of knowledge, because I don't have real experience with this. I am skeptical about using biological measurements like RNA-seq. But I'm more optimistic about high throughput devices, but that's also, I think, because I am more exposed to them because I know that many farms have all kind of accelerometers, milking robots and things like that. But that's what I think now. But I mean, this is a statement with very low confidence from my part. And I think that's pretty much it. I will be happy to answer any questions. Thank you for inviting me.
Thank you very much, Andres. Julia, can you take the floor? Thank you. I think you have activated the microphone, and then go ahead with the second presenter. Okay, I can go ahead, Julia, if you can speak. Oh, okay, that's fine. So Julia has some issue with the computer. Technology sometimes doesn't work. This is something that we need to take into account when we measure omics with some technology or accelerometers. So this will be one of the questions that I will ask you: how to some way to solve the problems of the technologies that sometimes doesn't work in this context. Okay, no, we can continue with the second presentation. Andrea Vergani. Thank you very, very much again, Andres. Please remain for the questions that will be after the second presentation. So, Andrea, can you share your presentation? Okay, good.
Yeah, I should be sharing. Can you hear me?
Yes, okay,
Yeah,
go
can you
ahead.
see the presentation in full screen mode, right?
Yes, okay, very good. Go ahead. Thank you.
Okay, I can start. So, first of all, thanks for having me here and for having the opportunity to present this work to the cost action community. So, I'm Andrea Mario Vergani. I'm a computer scientist and an engineer by training. I'm from Politecnico di Milano, and today I would like to talk to you about a work that originated from a collaboration between me and my department and the Department of Veterinary Medicine and Animal Sciences at the Università degli Studi di Milano, the University of Milan. And basically, this was the first approach, let's say, in which we as computer scientists, engineers, came across, let's say, the world of livestock farming and the data that it offers and the opportunity that it offers in the field of machine learning. So the topic of the talk would be the use of machine learning in livestock farming, and especially how to combine genomics and phenomics to make sense of the data that is today available to breeders, and sometimes it's not exploited enough. So the starting point is that nowadays there is big data available in most of farms or in a lot of farms, and this makes precision farming possible. Why? Because nowadays breeders have genotypic data available. They can genotype their herd. They have longitudinal phenotypic data. The focus of this talk will be about milking robot data and cattle, dairy cattle animals. So as you know, there is a large availability in farm, so within the herd, of phenotypic data that is continuously collected, for instance, by automatic milking systems that also collect environmental data. So, there is a lot of data that is available to farms and that can be exploited towards the achievement of precision livestock. And in this sense, when you have a lot of data, you can think about using artificial intelligence to make sense of this data and to really try to leverage the potential of this data that sometimes, as I was saying, is not fully exploited. So with AI, with artificial intelligence in livestock farming, you can think about trying to exploit some complex nonlinear patterns between the data to predict some kind of phenotypic value that you would like to predict for, let's say, herd management reasons, for production reasons, and so on. In this talk, we will focus about the prediction of the bovine milk production in the setting that I will show you later during this presentation. The point is that AI, is a great tool, is a powerful tool to try to exploit phenotypic and environmental data that is available to breeders, but nowadays it often, let's say, AI in precision livestock often, let's say, does not include genotypic data so does not take genotypic data into consideration. This means that, there are great achievements also in latest years about the use of AI to predict some kind of phenotypic values, for instance, bovine meat production, but it really rarely includes genotypic data or explicit genotypic data in the analysis. And so what we want to do in this work, and what I will talk to you in this talk, is how to use machine learning in livestock farming for phenomics prediction, explicitly including genotypic information in the model. So the goal, of course, is that if breeders have genotypic and phenotypic data available, so you would like to exploit artificial intelligence to integrate these omics together in order to get better predictions, and in order to better support the breeders' decision making. Because if you have good predictions, you can then breeders have some material for which to, let's say, start planning their herd management decisions. So this is what we planned for. So this is let's say, the pipeline that we planned to integrate environmental features and genetic features into a single model that was able to predict a phenotypic trait through artificial intelligence. So, as I was saying, we started from genotypic and phenotypic data. So we had environmental features available and we have the genetic data available. The point is that when you want to integrate genomics, which is high dimensional and complex, and phenotypic data, you need to start from genomics and extract some features that can be used in a machine learning model, in an artificial intelligence model. If you don't do that, you have too many genetic features, too many SNP values to work with, and the problem becomes intractable. So our idea was, we want to integrate genomics with environmental data, with phenomics data. First thing we have to do is to extract some genomic features, some relevant genomic features through a genomic feature extraction model. And once we have these genomic features, we can integrate them as features of a machine learning model to predict, in our case, the daily milk production. This talk and all the experiments we did were about daily milk production in a cattle breeding farm, but the phenotypic trait that you want to predict can be any quantitative phenotype, so it's not limited to production traits, even if it was, let's say, it can become more complicated for certain kind of traits to model the problem as we did. Given this, let me briefly discuss about the data that we had available during this study. So the data was collected under the GENOI project, which was a project based in Lombardy, Italy, that was about the genotypization and trying to get value from the genotypization of Holstein farms in Lombardy. We focused on data from a single farm, a single herd with more than 500 genotyped female cows under production. For these cows, we had daily records over 26 consecutive months given by the automatic milking system. So these cows were under lactations for 26 months. Of course, some cows enter lactation, some cows exited lactations, but we have data for 26 consecutive months for a total of 170K daily observation over 900 lactations. And for the same cows, we didn't have just milk production and environmental records, but we also had genomic records. So these cows were genotyped, and we had the raw genotype available on the SNP chip, and also the genomic breeding value. So for these cows, we had also the genomic estimated breeding values that was given by the Breeders Association. So for these cows, we knew more or less everything. We knew when the lactation started, when the lactation ended, what was the daily production for every day of lactation, which was their genetic breeding value, which was their genotype. So we had like a complete overview of the cow genetics and production. And this was available for 900 lactation. So we had a great data set available. And the target was, so the question that we wanted to answer was, how can we use machine learning to make sense of this massive amount of data with the goal of forecasting daily milk production? Why? Because this data was really available to breeders. So in a real situation, this is data that is available to breeders, but is sometimes, as I was saying, not used or only partially used. Well, we wanted to show that it's possible to forecast daily milk production better than what is currently done, exploiting this massive amount of data that is available within single herd. Just for you to know, just one slide, if you don't know how a lactation curve looks like, it's like this. So on the left in this slide, you can see a theoretical lactation curve. So a cow after calving, let's say, produces a quantity of milk that follows more or less the curve that is depicted on the left. So it has the lactation starts with low amount of milk, let's say per day, then it goes to a peak after a certain amount of weeks, and then it more or less linearly decreases to until the end of the lactation. This is what a theoretical lactation curve looks like, but the real data is much more noisy, as you can see on the right. So what we wanted to predict actually was a kind of lactation curve that you see on the right. So very noisy, does respect just a little bit what is the theoretical and the ideal behavior, but this is the kind of lactation curve that breeders are interested to predict, because this is the real lactation curve. And so our goal was leverage all the data that we had available, environmental data, genetic data, and so on and so forth, to predict the real lactation curve, so the real production of an animal day by day. As I said before, for using machine learning in this context, we had basically two steps to follow. The first one was to extract a limited set of genetic features starting from raw genotypes, and then insert these genetic features together with environmental features into a machine learning based model to predict the daily milk production. So for step one, so for the how to extract the genetic features, we decided to rely on the genomic breeding values given by the Breeders Association. So we had genomic breeding values available. If we didn't have, suppose that you start from SNP values, you estimate your genetic breeding values, and that single number is let's say, how genetically good is your cow to predict to produce milk. You use that single number instead of 100,000 SNPs as input to your machine learning model. So the machine learning model becomes much more simple because it cannot rely on 100K features, but it just relies on one feature, that is the summarization of the genetics, of the genetic importance in production of that cow. We used instead of estimating our own breeding values, we used the ones by the Breeders Association because they are much more accurate. They are based on large populations. They are based on state-of-the-art models that embed, of course, domain knowledge in animal genomics and so on. So this is the first chunk of information that we used. So on the genetic side, we used the genomic breeding values, and we coupled the genomic breeding values with environmental features in the machine learning models. We decided to use the parity of the lactation, days in milk, age at calving, and month of calving as features for our machine learning model. And so basically the problem was formulated like this. So suppose we have a data set. We have the data set of, we said 170K daily observations. So sample 1 to sample n is our 170K observation, n is 170K in our case. And basically the data set was structured as, okay, for every daily production record, it corresponds to a lactation, so to a parity, the cow in that lactation at a certain parity. Days in milk went to 1 for day 1, 2 for day 2, and so on. Age at calving and month of calving for that lactation, and then the genomic breeding value. And what we want to, and these are the input features, and then you want to predict the output feature, that is the daily milk yield. So basically, you want to the machine learning formulation is, okay, you want to say y, that is daily milk yield, yij is f of parity, days in milk, age of calving, month of calving, and the GABV and a. And the role of machine learning is to find the f, the function that best estimates, let's say, the daily milk yield based on data and on, of course, the features. So we had, again, one sample per daily milk yield record. We train the model splitting on animals. What does it mean? It means that we basically, when we split, let's say, some train animals and some test animals. This means that we tested the model on animals that were never seen during trainings. So this is what happens in real situations. Suppose you have some newborn calves. What the breeder wants to know is what will be the production of these newborn calves, for which I never had the production data. If you already had production data, you could use that data to infer what will be the production like, let's say, in the next lactation. But what we wanted to achieve is, okay, for a newborn cow, you have never seen the cow producing. Can you say something about its production in the future, in the first lactation, and also in subsequent lactations, based on its genetics and on the age when calving will start and the month when calving will start. Given this formulation, if this formulation is clear, you should know that this is a regression task. So we want to basically predict the daily milk yield, which is a continuous value, and so we assessed the prediction performance of several machine learning models for these regression tasks. Coming to the results of this experiments with our data, first thing that we saw is that machine learning clearly outperformed linear models for the forecasting of milk production. This means that, as we know, the relationship between the features and the output, so between the features and milk production, are non-linear, and so they cannot be fully captured by a linear model, while they are captured by a more complex model like a neural network. In all these examples, in the results section, I will talk about neural networks because they proved to be the best among the tested machine learning models for the prediction. So machine learning outperformed linear models, as you can see from the picture, we had a day-by-day error between prediction and real values, about 5 kilograms per day for the machine learning case, while we had 7, 8, let's say, average value for the linear model. So the machine learning model significantly outperformed the linear model in prediction, in average prediction, but also in prediction day by day, as the plot shows. And coming to the role of genetics, because we explicitly wanted to include genetics into the model, we explored what is the role of genetics in this setting, and we found out that genetics plays a crucial role. So if we didn't include genetics in the model, we would have lost 8% of correlation in the test set. So, I mean, genetics plays a crucial role, a significant role in prediction. Predictions without genetics are significantly worse than predictions with genetics. So this is the importance of including genetics into the problem formulation, and including genetics in the way that is as simple as possible. So in the lowest number of features as possible. So in our case, as a single feature, genomic breeding value, because it can really boost the machine learning performance. Another thing that we explored is, machine learning can easily also incorporate non-traditional features like number of milkings, concentrate consumption. What happens if we include them? And so if we extend the model, we see better prediction. So up to 20% of gain in the correlation of in the test set with respect to the baseline model, that is the model that was trained only with traditional features. So you may argue that knowing concentrate consumption day by day is complicated. It's true, and it's not also it cannot be regulated by breeders. But we found out that the predictions are even better when these values of non-traditional features are monthly averaged. And maybe we believe that it can be possible at least to enforce by breeders what is the monthly average value of concentrate consumption, and the predictions are even better than this shown in this slide. You may wonder now what a prediction looks like with machine learning. So for an never seen bovine, what is the, let's say, prediction performance on a real lactation curve? And these two plots show it. So the blue curve is the real lactation curve that was never observed, of course, during training, but we use just for testing purposes. And you can see that the brown curve, that is the prediction by machine learning, by the neural network, significantly outperformed the orange one, that is linear model prediction performance. And if you include additional predictions, you get really, really, really close to the real behavior. So beforehand, you can predict really, really accurately the future lactation curve by a bovine that you have never seen a day in production. Coming to the conclusions, we believe that this methodology, and especially AI in livestock breeding and in this setting, can help predicting, let's say, traits even before first calving, especially if you have a genotype available. We know that genotype is available after birth. You can easily integrate genotype information into a machine learning setting, and you can predict a trait even before first calving, or even at birth, let's say. This can serve as decision support to daily cattle breeders, and especially for herd and reproduction management of the herd, let's say, it can be valuable. Something that we are trying to do right now as future step is the picture you see on the right. We are trying to, let's say, simulate lactation curves if calving happened, let's say, 2 months before or 2 months after, and see what happened. And see what will happen comparing with the real curve. This will inform breeders, let's say, you can wait 2 months more maybe for calving. If you can wait, you can think about waiting 2 months more to have let's say, more production than calving now, let's say. And this can really become a great AI-based decision support tool for breeders. Of course, our approach has limitations. One was mentioned in the previous talk, that is overfitting. We just add data from one herd, and this will not translate well to other herds. So the methodology will, but the results, the specific results will not. We didn't explore the time series nature of the problem, so we can get even better predictions if we did. And of course, you can think about extending to other traits and domain to improve the sustainability, the conditions, and the welfare of animals. If you just want to remember, let's say, one message from this talk, and that I believe is important, is that artificial intelligence is a powerful tool and will become a powerful tool for phenomics and for precision livestock farming. But to make it possible, we need integration of several things: of data, genomics, phenomics, omics in general, of methods, animal genetics, animal breeding, machine learning, computer science, and so on, and of course of expertise. So I think that this cost action is really, let's say, a community where we can join expertise in order to, let's say, go towards precision livestock and go towards the full exploitation of omics data and technologies that is today available. So with this, I thank you for the attention, and I would like to thank especially Marco Masseroli and Alessandro Bagnato and his team for this joint work, and I'm happy to take any questions if you have.
Thank you very much. Can you hear me now?
Yes.
Yes. Great. Thank you for your talks, Andrea and Andres. I would like to allocate a few minutes for maybe one or two questions because we are a bit over time. So if somebody from the audience has any question, please raise your hand and feel free to interact with us and our speakers. Yep. Otherwise, I would maybe have a comment or a question, or maybe it just so I feel like the linear or what models we are currently using, they're like one solution that fits all. And I like what I learned from the talks today is that if we are adding other layers of information or bringing in AI, I think we are at this stage where we are maybe going by experiment, by scenario to scenario in an effort to find an overarching methodology. So similar to the linear models that we are using in practice. My question is, when do you think these issues will become available in the application? So for the genetic evaluation or what we are doing currently. Yeah.
It's a question for whom? For Andrea or for me?
If you would like to add on this, Andres. Yeah.
What I talked about, the introduction of omics, that thing would be useful when people start. First, it needs to be something that is useful, and second, people need to start taking those recordings.
Yeah.
And a second answer is that our customers are breeders and people in the artificial insemination companies, so they need to get used to that. And it needs to be reported in a way that it's useful for them. I mean, I learned this recently because, well, if you work for dairy cattle genetic evaluation, you cannot just call someone and explain. It's a bit more complicated. So there's an intermediate job of explaining and showing them how to use. But I mean, it can be, for instance, a software that does machine learning to predict a cow's lactation curve. It can be, but you need to, I mean, we need to prepare the tools for people to use them.
Yes, I think it's going to be a very interesting shift, as it was with genomic selection as well. So in terms of acceptance, yeah. So I think the future looks very interesting. I would say. Okay, we have somebody raised the hand, so we can take. Yes, Luca, would you like to add something?
Yeah. Well, just a comment on omics. Actually, omics or maybe also sensor technologies that could add additional level of complications. Some of the features might not be available in all individuals, or when they are available, they need to be available for many modeling, and or maybe the tools sometimes doesn't work. So there is probably the need also to integrate into the models some a little bit elements that might deal with imperfect data that might be quite frequent in some cases, I guess. So that's could be also another element of discussion, potentially.
Yes, thank you for the addition. So I think we have time to take the question from Francesco. I think he was.
Yep. Thanks. Good evening or good morning, wherever you are. And thanks for the nice talks and thanks for organizing this. I have a question for Dr. Legarra, and it's a bit of a thought-provoking question. It's not really my point, but let's say. So in your slides, you have shown several times that there is a genetic component of the phenotype and a genetic component of the mediator. And then there is the link between one and the other one, and the mediator or the intermediate omic shouldn't use the causal inference terminology. Let's call it an intermediate omic. So my provoking question is, how do you see leveraging the covariance between those two genetic components and simply using a multiple trait model rather than having to have two systems of equations that basically build on each other?
The thing is that you cannot really have a multiple trait model because you don't know how to correlate the omics to the phenotype because you have many omics. So what we do is essentially a modified, it's equivalent to a kind of multiple trait modeling, in which we force to send all the covariance between omics and the phenotype that we want to predict into this mediated thing. And the part that is not covariance, we send it to this residual thing. So it's a different decomposition, but it's essentially a multiple trait modified model.
Yeah, right. Thanks. I tend to agree to that, but yes, it's a different way to put it down.
Mm-hmm.
But essentially, it's extracting the same information.
Yes.
Thanks.
Thank you very much. I think in the interest of time, we'll have to stop here. I apologize for the ones who had the questions that have not been answered, but I think you could directly contact the speakers. And I would like to draw your attention towards our cost action. So we are cost action focusing on livestock phenomics. And we are in the second year, and we are looking to involve young researchers or researchers in the field and innovators. And if you do have interest to follow our work or to join our efforts, please use the QR codes. We are also very active on social media, so you can easily follow us. With this, I would like to thank you for your presence and wish you nice holidays, Merry Christmas for the ones who are celebrating, and a great year ahead. All the best.
Yeah, Thank you. Thank you very much. Thank you for the two speakers. Thank you very much. We'll be in touch.
Thank you.
Bye.